As time progresses, application scientists face themselves with ever-increasing volumes of data. To deal with this deluge of incoming data, some have turned to techniques like compression to reduce the footprint of the data when they move it or store it. Historically, they've done so using lossless methods, like zip files, which perfectly preserve the data before and after compression. The problem with this, though, is that these methods tend to perform poorly when used on floating point data that is pervasive in high-performance computing. This then led them to turn to lossy formats, such as JPEGs, which only approximate the original data being compressed. These methods tend to perform better in terms of compression ratio, but they're typically difficult to integrate into scientific applications because it's hard to understand what data is being lost and how much of it is being lost. This has led some to develop error-bounded lossy compression methods, which combine the benefits of lossless compression with some of the benefits of lossy compression, allowing users to determine exactly how much error will be allowed to be introduced into their applications. But error-bounded lossy compression itself even leaves much to be desired. There are inconsistent interfaces, difficulty in configuring them, and there's a lack of tooling to really understand what its effects are. My name is Robert Underwood. I'm a PhD candidate at Clemson University, and today I'll be presenting research that I've done working on my dissertation entitled Approachable Error-Bounded Lossy Compression, under the guidance of my advisors Dr. Amy Apon, Dr. John C. Calhoun, and Dr. Frank Capello. My dissertation aims to make error-bounded lossy compression approachable by providing a consistent interface, automatic configuration, and tools to better understand the effects of error-bounded lossy compression. Let's begin with my work to help make the interface more consistent. Compressors and analysis codes really need common interfaces to better interop, and without these interfaces, a variety of features have developed independently on different compressors that can't really be used together. Our solution is libpressio. Libpressio provides a common data abstraction, common definitions for standard bounds, and strictly defined parallel semantics to enable users to effectively share resources in their parallel codes. While we were developing libpressio, one of our key insights was that if we included a concept we call a metacompressor, we could very quickly start to address the problem of the proliferation of tooling, making it easier to use the same kinds of tools on a variety of different compressors. These metacompressors can be things such as auto-tuners, parallel runtimes, as well as pre- and post-processors. These allow to have one implementation solving the problem for a variety of different compressors. libpressio has already begun to solve a lot of problems, and you can find information about it on the libpressio webpage linked here. We're not done with libpressio. There's a variety of different tasks that we think we can better address. One is the allowing of asynchronous processing, the introduction of better support for sparse problems, and the use of accelerators such as GPUs or FPGAs. So now that we have this consistent interface, what can we do with it? Well, one of the first problems that we wanted to tackle was the automated configuration of compressors. And we've really been working on this work in 3 stages. The first stage we call Frazz, fixed ratio compression. In Frazz, we asked, can we tune a compression experiment with a control loop to bound the compression ratio? The goal here is that users commonly ask, what is the best error bound that I can get for a desired compression ratio? And our approach was to use the libpressio compressor interface as well as some derivative-free optimization techniques to formulate a compression problem as shown in figure 2. As you can see, however, naive approaches to this problem would be unsatisfactory. The relationship between the error bound of the compressor and the compression ratio achieved is not monotonic. It's not even necessarily mostly monotonic. It's a very noisy process, meaning techniques such as binary search were likely to perform poorly, needing a more robust mathematical solution to approach the problem. We found that even when using these more robust mathematical approaches, when amortized over an entire data set, tuning only takes about 2 times longer than what an oracle that simply knows the answer was able to achieve. We found that fixed ratio compression had a higher data integrity than the pre-existing fixed rate methods. And we found that the runtime tended to scale with the longest task. We also found that utilizing relationships between time steps and other similar problems was key. All of this kind of led us to think about a redesign when we developed libpressio opt. In libpressio opt, we asked, can we extend Frazz to bound simple user error metrics more generally? So what we did is we converted Frazz into a libpressio metacompressor, allowing the techniques used in Frazz to be applied to any compressor that supports the libpressio compressor interface. Use the libpressio metrics interface to gather information on the data, allowing users to create metrics that model specific concerns that they have. And then we added a number of performance optimizations such as iteration, early termination, as well as supporting new max and min search modes. One of our key findings from this work is that opt, by taking advantage of these additional optimizations, was able to perform with less overhead than Frazz, while also extending this work to support more general notions of what users care about, such as maybe bounding the SSIM or the PSNR, two commonly used metrics in the climate community. So where are we going from here? Now we want to look at more complex applications, so to hack code. Hack is a complex cosmological simulation, and it has a number of metrics that they care about, one of which would be things like spectral error. So they want to bound the distribution that occurs in Fourier space. No current compressor really bounds a metric similar to this. So what is our approach? One, we will implement the spectra as a libpressio metric. Then we will explore ways to compare those spectra. We've already identified a number of different statistics for doing this. And then we want to adopt libpressio opt to operate on multiple buffers simultaneously. One key feature of the hack code is that it actually has several different buffers that all need to be analyzed collectively in order to really appropriately set an error bound on any one of them. This will allow us to solve for the maximum compression ratio such that the differences between the spectra are acceptable. As future work that we're aiming to look at in this calendar year and into the next, we want to look at true multi-objective compression rather than simply a constraint on the objective. We also want to improve the search algorithm and look at ways to better improve the compression task scheduling. With all of these techniques, for understanding the configuration of compressors, it's also important to make sure that we provide tools for understanding the effects of compression. One example work from this is our work looking at error-bounded lossy compression in machine learning and artificial intelligence applications. What we wanted to ask are, what are the trade-offs for compressing training and validation or testing data to better save storage space? Our approach was to use libpressio opt in conjunction with libpressio to generate Pareto curves, basically points that dominate the other points around them. Basically, what's at each point, what is the best compression ratio we can achieve for a given loss in accuracy? With this work and with these tools, we are able to find that SZ and ZFP outperform common methods used in the AI and machine learning space, even for imbalanced problems, which tend to struggle with sampling-based approaches. In some cases, error-bounded lossy compression had even better results than doing nothing at all due to reduced overfitting. In the future, we'd like to look at applying these same kinds of techniques, looking at what we could do between the CPU and the GPU to make data transfers between these devices more practical. But that's not all that we can do with these kinds of tools. We have a variety of different applications and frameworks that we've developed, such as libpressio tools for testing workflows, libpressio error injector for doing noise injection studies. We have libpressio predict for high-fidelity proxy models for compression that we've all developed to a point where they're prototype but functional. And then we've also defined bindings for libpressio for Julia and Python. In summation, error-bounded lossy compression has the potential to be transformative in a wide array of domains if application scientists have the tools that they need to interface with new compressors on their data and have tooling to support them along the way. This work provides a strong foundation to enable further research in air-bounded lossy compression and enable improvements to scientific applications. If you have any questions, feel free to contact me at robertu@g.clemson.edu.